When you learned in school about vectors and operations on them, you specifically learned about the cross product. This operation takes two vectors in R3 and returns another vector in R3. But you might be asking to yourself, why does it has to be specific to R3? Can it make sense for other dimensions as well, like R2 or R4? First, let's start from scratch. We're going to ask ourselves what is the motivation behind a cross product in the first place. Let's consider two vectors in R3. If they aren't parallel, then there must exist infinitely many vectors of R3 that are orthogonal to both of them, and they must all lie on a line passing through the origin. So, if we can just find one non-zero vector among them, we can express all the others as its multiples with scalars. The goal of the cross product, then, is to return such a vector. Let's call u and v our two initial vectors, and w the one we want to be orthogonal to both u and v. Let's point out that w is unknown, as well as its components. The most straightforward way to find such a vector would be to solve a linear system of equations as follows. But this is quite painful to do in the general case. So the idea behind the cross product is basically a technique to solve this problem more easily. We first consider the following determinant. It has the previously defined vectors u and v as its second and third columns, while its first column is made of unspecified variables alpha, beta, and gamma. We can develop it using the first column as such. But then we notice that this expression can be reinterpreted as doing a scalar product between the vector alpha, beta, gamma and a new vector with determinants as its components. Let's shorten this chain of equalities. The trick then is to attribute the value of the vector u to the first column. Doing so, the determinant at the left has to be 0, because it has two identical columns. By transitivity, this means the scalar product at the right must also equal 0. We can do the same trick by attributing the value of v to the first column. The same logic then applies. What we've just done showed that the new vector we constructed with determinants as its components is orthogonal to both u and v. So we could define the cross product of u and v as this vector. But there is another way to notate this vector that will make it more explicit how to generalize the cross product to other dimensions. First, we just separate the components of the new vector as such. Now, let's notate the canonical vectors with letters instead, or rather these letters, easier to generalize to other dimensions. But then we notice that this expression is the development of the following matrix. And this is how we are going to define the cross product in R3. Can we do something similar in R2? Let's consider this determinant again. If we just remove its last column and its last row, we get this one instead. What seems weird at first glance is that there only seems to be one vector as an entry to this operation, which is to say the vector AB. Let's just give it a quick shot. When we develop it trying to get a vector, we get the vector b minus a. We notice that the scalar product of AB and b minus a is 0, which means that they are orthogonal. So the cross product in R2 would just be an operation that takes a single vector from R2 and returns a single one that is orthogonal to it. This should make sense, because in R2, all it takes is a single vector to limit all its possible orthogonal vectors to lie on a single line passing through the origin. So this operation seems pretty legit. But how are we going to notate it if it has only one entry? Let's make a brief side note on notation. Let's take a binary operation, like the usual product on real numbers. It is most common to use infix notation to write it, which means to place the operation symbol between the two entries. But another way would just be to write it as a function with two entries or arguments. This is called function notation and can have any number of entries, unlike infix notation, which is for binary operations. So when it comes to define the cross product in R2, we can use function notation and just put the cross symbol in front of the vector AB. Well, this looks pretty good to me. Now, what about for R4? Let's process similarly. We take the same determinant as before, but now add both a column and a row instead. So we are now dealing with an operation with three vectors of dimension 4 as entries. I will let the development that will explicit the 4D vector output to you. Writing this operation using function notation, we get this. Again, looks pretty good. I'll let to you how to formalize the cross product to dimension n. So we've basically answered the title of this video. But for those who saw my previous video, you might say to yourself, is it still legit to call these operations products? Isn't multiplication a binary operation? Well, let's revisit what I previously said. If we have a set A and two binary operations on A, if one is distributive on the other, from both the right and the left, we say the former is the product and the latter is the addition. This, in fact, describes the binary multiplication on a single set. Can we generalize this so to include multiplication with other numbers of entries? To help us do the transition, let's just rewrite the product with function notation instead, but keep the addition with infix notation. We see that the product is a function such that if one of its entries is a sum of two elements, we can split the whole into a sum of two products. But such a condition can easily be described for a function with a number of entries other than 2. So let's define the unary multiplication on a single set. If we have a set A with two operations, one binary and the other unary, we can call them addition and multiplication if the following condition holds. So the product of the sum of two elements is the sum of the products of each element. Let's note, for example, that the function that returns the opposite of a number would be a unary multiplication under this convention, and so is the cross product in R2. For the general case, we would formalize it this way instead. So we let the addition be binary and the product be n-ary, and we want the following condition to hold. This basically means that if one of the entries of the product is a sum of two elements, we can split the whole into a sum of two products as well. So, for example, the cross product in Rn plus 1 would be an n-ary multiplication. So that's all I've got to say. Hope I brought some light on some mathematical notations and conventions. This was the second part on a 3-part video series on the general notion of product. The last video is going to be an alternative approach of mine to complex numbers. So do not forget to subscribe if you don't want to miss it. Thanks for watching.